Very happy to have you here at this afternoon's CPEP seminar series. And happy early Earth Day, which I guess is officially tomorrow. Um, I do want to remind everyone, though, that this is part of Earth Fest. And so if this is your first activity in Earth Fest, welcome and thank you for that. Alessandra has just put in the chat the website for more events. There are events for going on all week this week for EarthFest. So please do take a minute to check those out and participate in as many as you are available for. So for the CPEP seminar today, we have a wonderful set of four flash talks, about 10 minutes or so from each of these four different speakers. And so we're very much looking forward to these. We have four speakers. We have Paul Buchmann. He's at the State Climatology Office. We have Chris Kucharik. He's the director of the Wisconsin Environmental Mesonet or Wisconet. We have Liz Maroon, assistant professor in AOS. And we have Luke Zoet, who's a professor and chair in geosciences. We are going to go through all four presentations and then take questions afterwards. We should have time for that. But if you have a question and you're thinking about it during one of the talks, feel free to add that to the chat at any time that you want. And then we'll go back and we'll review those after we've finished with all four speakers. So again, thanks for being here and excited about these talks. And Paul, I will turn it over to you.
Great, thank you so much. Let me just share my screen. Um, Here we go. Thank you. Yeah, so I will be talking briefly on causes of flooding on Wisconsin's Rock River. So, just as a brief introduction to the Rock River, if you're not familiar with it, the head of the Rock River lies about halfway between here and Milwaukee. And there's a region here, circled in red, that has been getting flooded and that the flooding has been getting worse. And so we've been called in to study this. Who's getting flooded? It's the towns of Lebanon, Astrupan, Hustisford, and Ixonia, as well as the surrounding farmers and farmland. And so just looking at the how the river has been changing, we can look at the average daily flow every 15 years. So we have records back to the early 1930s. And so looking at the flow from 1935 to 1949, you can see kind of what you might expect for a river in Wisconsin, being that you get a peak in the spring, but then it kind of goes back to more of a base flow, kind of a lower flow during the rest of the year. So you might expect that there might be some flooding during the spring, um, but then not during the rest of the year. Looking at 1950 to 1964, we see a little bit of variability in when the peak flow is, but overall it looks fairly similar. 1965 to 1979, then again very similar. So a little bit of kind of that variability in when and how much peak flow we get, but really the rest of the year is very similar in terms of flow. 1980 to 1994, we're starting to see something a little bit different. So the peak hasn't really changed in magnitude, but how long that there's that peak flow um, is definitely increasing. So you can see here the width of that peak is wider, and then you see something kind of interesting too in the fall. There's more flow than in the last 45 years before that. Uh, 1995 to 2009, again, we see that width of the peak is really increasing as well. And then we have this huge spike in the summer. And so a lot of that was from a historic 2008 rainfall event and flood. But even without that particular year, you still get a huge peak in the summer. Um, and then finally, for the last 15 years, 2010 to 2024, the peak has really risen. It continues to widen, and we get a lot more water in this river kind of all of the time. And so if we look here at this plot in the top right, we can see that the annual discharge of the Rock River from 1932 to 2025 um, has tripled in the last, 90 odd years. So flooding has gotten much more frequent, much more intense. And so this plot on the bottom right here shows the number of days that this particular area sees flooding. And so you can see in the 1930s to 1960s or so, the number of days that there was flooding was, about a month, maybe a month and a half, and every like 2 or 3 years. Whereas now um, they can get sometimes up to 4 months of flooding per year, and it floods basically every single year. So the flooding has gotten more frequent, more intense, and the timing of the floods has changed. And so now it can flood all year round, whereas in the earlier part of the record, it really only flooded in the spring. And so then the goals of this work is to figure out why it's been flooding more. And so we have been looking at how precipitation has changed, how land use has changed, and then how those two pieces interact. And then the pieces that of this project that the farmers and the towns really care about is, can we do something about it, and how might the river flood in the future? And so looking at the precipitation changes, we have data going back to 1950. And so the annual precipitation over this Rock River Basin has increased by about 6 inches since 1950, from about 30 inches to 36 inches. And not shown here, but every season has also seen an increase. In addition to the annual precipitation increase, precipitation has also become more intense. So this plot here on the bottom right shows the number of 2-inch and 3-inch rain events over the course of 3 days. And so you can see that, starting in 1951 to the present, the number of 2-inch events here on the top has gone up to, somewhere between 5 and 10 events per year. And the number of 3-inch events, so those are the really intense events, also shows a notable increase. In terms of land use changes, one factor that we think might be important is artificial drainage on farm fields. So these are systems that quickly remove water from fields after heavy rains. And I do want to emphasize that that on an individual farm, these systems are really important for farmers. They really help increase the yields of a particular field. Um, but they do remove the water from the fields. And so where does the water go? I mean, it has to go into the river, right? And so how do we think that this affects the river? Um, we think that this will create a faster response to rain, which is called flashier. So you can think like flash floods. And we think that ultimately less water will get evaporated from the soil, which means that there's more water in the river. Unfortunately, there's very little data on how much artificial drainage is present in this region, but anecdotally, drainage on farm fields started in about 1980 or so. And so when we look at the effect of land use changes, that's kind of our cutoff. And so looking at the amount of river discharge per kind of unit of precipitation, we can see in this plot here, pre-1980 is in red and post-1980 is in blue, along with their best fit lines. And so you can see that, for some of the post-1980 years when we've gotten a lot of rain, but also a lot of river discharge, those plots would be up here in the upper right. But we can see kind of focusing on the middle part of the plot, kind of the 30 to 35 inches of precipitation. That'd be kind of more of a moderate amount of annual precipitation. We can see that the blue points are essentially all above the red points, which means that for even these kind of moderate precipitation years, the amount of river discharge to precipitation has increased. And so the next step in our analysis that we are currently working on is to construct a rainfall runoff model to more accurately determine how changing precipitation and land use interact. And so, again, what the farmers and towns care about is what can we do about the flooding? So this is some of the work that we've been doing with the civil engineering department here at the university. And we've come up with three possibilities. The first one being to dredge portions of the river. Unfortunately, that's probably going to be more expensive than the flooded land is actually worth. Another option is to use the upstream lake as water storage in the spring. Um, that might have some flood reduction in some years, but unfortunately, the lake really just isn't very big, so it just doesn't have that much storage. And also, the people who live on this lake don't like this idea of having their lake being used as a water storage. The third idea is to restore some areas in the basin to wetland. That's in some regards the most realistic option, but that will be expensive and will probably take something like 20 years to actually fully implement. And then looking into the future, we looked at 22 downscaled CMIP6 models with three realizations of each model. And so what we're interested in is precipitation and magnitude and trend over the basin. And so looking on the annual time scale, so here on the kind of the left part of the plot, we have the observed annual precipitation. And then here on the right out to 2100, we have an estimate of the maximum precipitation as well as the minimum here down in brown. And so we can look at each season as well. And so in winter, we can see that the possible maximum precipitation is increasing. In the spring, it is also dramatically increasing from something like an average of 10 inches to potentially up to like 15 or 20 inches in a given spring. In the summer, we see an actually a slight downward trend in the future. And then in the fall, it stays fairly similar. And so just in conclusion, we see that precipitation is drastically increasing in every season. We can also see the effect of land use change, even during years with moderate precipitation. Um, Solutions to mitigate the flooding are neither cheap nor quick, and under future warming, the flooding may change, but it is probably not going to stop. And I'd like to acknowledge some of my co-authors and the Institute for Rural Partnerships. Um, Thank you. That's all I have.
Great. Thanks very much, Paul. Really appreciate that talk on the Rock River flooding. Again, just as a reminder to the audience, if you have any questions, you're welcome to either save those till the end, or you can put them into the chat, and we'll review those. Next up, we have Chris Kucharik. Chris, I'll turn it over to you.
Is that showing up okay, or do I need to switch the display?
That looks good for us.
Oh, okay. All right. Thanks. Yeah, I'm Chris Kucharik, a professor at UW in Plant and Agroecosystem Sciences and the Nelson Institute. So I'm going to talk about Wisconet, a growing network, weather and soil monitoring network across Wisconsin. This work has been supported through the Rural Partnerships Institute, funded by USDA, as well as WARF. So the first thing I want to elaborate on is just the mission statement of our Mesonet here. We're trying to build and maintain an elite network across the state that allows timely and accurate data and decision support tools for farmers, resource management, research, and other industry decision making. And to this point, our network is 78 stations, roughly one in each county. There are a few areas in the Central Sands and in some of the cranberry growing regions that have a higher density, as well as Door County, which is supporting apple and cherry production there. But we're collecting 12 different variables every 5 minutes across the network. More specifically, we're measuring the generally a complete suite of meteorological data that includes temperature, dew point, relative humidity, rainfall, liquid precip. So we don't do frozen things like snowfall and that. So this is just liquid form precipitation, solar radiation, wind speed direction, barometric pressure. We have leaf wetness sensors at each station, which are used in disease modeling that helps support some of our growers in the fruit industry. And then we're also measuring soil moisture and temperature down to 1 meter at 5 depths. So at 5, 10, 20, 50, and 100 centimeters. So I'm throwing this slide up just, this was written several years ago, this article on the left. And at that time, it was showing, the importance of Mesonet. So mesoscale meteorology is a phenomenon that's generally happening on the scale of tens of miles, let's say. And, the quotes on the right generally show that, the National Weather Service greatly depends on these timely data for issuance of warnings, severe weather in their forecasting. These data help parameterize the numerical weather prediction models that get run every day across the country and support all of us in our daily lives. Um, so at that time, there were, I think, around 34 states or so that had mesonets. So obviously now Wisconsin has one. In the last year, both Arkansas and Tennessee have also added mesonets. In fact, the state legislature in Tennessee most recently allocated multi-million dollars of funding to help support that with annual support thereafter, which is very encouraging to see states step up and help support these networks like that. So the benefits of these data are really wide-ranging. So obviously, the weather data drives our daily decision making in society and the economy. It can help improve our public safety as well as our emergency management planning. I already talked about the ability to improve the accuracy of weather forecasts and assist in warning issuance. Can also assist in transportation planning and decision making. Can help utilities plan for electrical and natural gas demand. Obviously, there's some K-12 connections for STEM education, as well as supporting research that's taking place across universities. More specifically to the ag community. So this is, a big thrust of what we're doing here. So we're able to provide the farmers, researchers, and crop consultants with real-time weather data and decision support tools to help improve productivity, increase resource use efficiency, increase their profitability, and then simultaneously reduce environmental impacts through those tools. If you want to read a little bit more about that connection to ag in the state, there was a great story. The University of Communications worked with us last year on this story that went live in December on the news.wis.edu website. And it's great in there because they have video and quotes from some of the farmers, particularly in the cranberry growing region and a few other places that demonstrate how they use these weather data in their daily decision making right on their phones and tablets. So I encourage you to go and visit that if you have time to learn more. So, overall, there's a lot of, thinking in how these weather networks can help protection of crops, property lives, and, while supporting research. So the soil moisture data, not every state mesonet has this information, but it helps provide support to the weekly updates of the National Drought Monitor. That helps to directly support drought and disaster assistance by knowing specifically, just how severe the drought was and being able to provide in situ confirmation through observations of what farmers were experiencing here. The Weather Service is already using Wisconet data. I have a story from, I think it was February of 2024. There was two tornadoes that occurred in the southeast part of the state, and I know firsthand from hearing from folks at the Milwaukee Sullivan office that they were looking at our data at that time to understand whether the atmosphere might be favorable for tornadic thunderstorm development. So there's lots of those stories all over the country, like I showed on one of the previous slides about the importance of these to the Weather Service. And then obviously we're helping support scientific research, and that spans lots of different segments of our university, from crops, soils, meteorology, entomology, animal and dairy science, and the list goes on and on from there. So if you want to read a little bit more about our ability in helping to build a more resilient Wisconsin to the types of things that Paul had just shown in the Rock River, area in southern Wisconsin here, this story was done and appeared in the January 2025 issue of Wisconsin Counties. So you can get online, Google that, and search and read a little bit more about Wisconet and what we're doing. The great thing is that all these data are free. And the website has gone through several rebirths over the last 3 years with improved features and tools. And I encourage you, I guess, for all of the almost 60 people on this call now, if you could do me a favor, go to wisconet.wis.edu. And if you're not already, use these data. Tell your friends, tell your families. A lot of people don't know, what a mesonet is, or definitely what a Wisconet might be. But these data will blow you away if you have a chance to go online and start playing around. You can choose your favorite station. It'll choose a station that's nearest you and help provide you with timely and accurate data updated basically every 10 to 15 minutes in real time. So last but not least, I have the privilege of helping lead this team, but honestly, I'm just the guy who writes the annual reports and finds the money to keep the funding going and making sure we're meeting our mission and our vision. But we have a team of engineers, web developers, and researchers that really get the job done and have done an amazing job the last 3 years standing this up. So I'll stop there and hand it off to our next speaker. Thank you.
Great. Thanks so much, Chris. Really appreciate the updates on Mesonet. Liz Maroon is our next speaker.
Can you see my slides?
Yes.
And hear me? Great.
Yes.
Hi, I'm Elizabeth Maroon, Liz Maroon for short, whichever you remember is fine by me. So I'm going to change the vibe up here. I'm an assistant professor in the Department of Atmospheric and Oceanic Sciences. I'm a climate scientist and physical oceanographer, and I think at much, much bigger scales than our past two speakers. So I want to start with this really lovely painting of what's called World Ocean Floor. And this is an artistic rendition of the first map we had of the bottom of the ocean by Heesen and Tharp. And I'm not going to get into the story of Heesen and Tharp or Marie Tharp, but if you have time after this, I highly encourage you to Google Marie Tharp because she's super inspirational. This is the map she drew. They got, and you can see just the texture of the bottom of the ocean. This is the first time we had, understanding of what that texture looks like. So a couple of big features, like you see this big spine, this huge mountain range going down the middle of the Atlantic Ocean. So one day I was sitting there thinking, I know there's a lot of old studies from the 70s and 80s using simple ocean models to try to understand it, but I wonder if anyone's done anything recently on it in a very realistic manner. So like in my graduate work, I'd done a lot of thinking about what do land mountain ranges do to climate. And this has got a really long history of people doing experiments where you take out the Rocky Mountains or the Himalaya, the whole mountain range to see what does the circulation. And so here I've got an example from HELD 1983, one of those early studies from one of the greats in atmospheric general circulation. And I've kind of sketched out what happened. So here, let's orient ourselves. Here's North America. Here's Eurasia. And so in this simulation, what he did in a fairly simple model was he took out Himalaya, and what it does is it spawns these high and low pressure systems that are on a near planetary scale, and it changes up what the jet is doing, where you have storms moving. So you get a circulation that anomalously goes this way, and another circulation that anomalously goes that way, but it spans way farther than just where the Himalaya are. Same thing for the Rockies. So here's the simulation where you move the Rocky Mountains. And you get a wave train coming off of North America where you get anomalously more high pressure here and anomalously more low pressure there. So you get a big change. And I was thinking, well, somebody must have done this in the 80s with the ocean circulation too. Somebody must have removed one of these big mountain ranges in the bottom of the ocean, so the Mid-Atlantic Ridge or these Pacific Rise. And I remember saying, okay, let's go find this. Let's see who's done this. And I found lots of idealized simulations where people are using, square boxes and Gaussian ridges, very idealized. But I couldn't actually find a simulation where someone had done the equivalent of what Isaac Held or John Kutzbach had done for atmospheric planetary waves. It's like, wow, okay, this is pretty cool. Let's, I found something that seems like a pretty big idea that hasn't been touched that should have been done in the 80s or 90s. So that's super cool. So that's what I'm going back to do is there's lots of folks who've done stuff adjacent to this, like using idealized simulations, but I want to do it with the full complexity that you can use. So using a whole climate model, or in this case, an Earth system model that is as complex and cutting edge as the kind of things you use in the IPCC report. I want to prove without a doubt that this does matter for climate and the ocean. So I'm using what's called the Community Earth System Model version 2. And basically what this is a bunch of global models. So at every location for each of the components of the Earth system. So we have an atmospheric model, which is very, very similar to what a weather model is. And then we have other models like an ocean model that basically does ocean weather. And then other components, so you have a sea ice model, a land ice model. So that means glaciers and ice sheets. And then they're all coupled together and exchange information every depending on your time step, every day or couple of hours. And so, for example, the atmosphere needs to know what the ocean's doing. It needs to know, is it warming or getting cold? It needs to know, am I getting some moisture from evaporation or am I raining? And so that's handled by this driver in this middle, this coupler. And so what makes this an Earth system model and not just a global climate model is these little green boxes down here. This model has fairly simple representations of ecosystems. So what's called biogeochemistry. And so you've got a representation of life that is impacting the physical ocean system and vegetation that's impacting the land system. So that's what makes this an Earth system model. So the idea I had is, okay, let's go and we'll start with our existing control simulation that they've already made for this model. And I'm going to remove the Mid-Atlantic Ridge. And so here's the two simulations we got. We've got a control simulation and then what I'm calling flat Atlantic, where basically the bottom of the ocean, the Mid-Atlantic Ridge is gone. So it's like I went latitude by latitude and I scanned it out going from one abyss to the other and just flattening it. And I did that all the way down to about 20. And the reason I did that is because we have theoretical expectations that north of 40 is where we should see the biggest impact. So I just kind of went a little bit further in that. But that's a choice we made. We can go back and remove the whole Mid-Atlantic Ridge some other time. So I did, this is the workhorse version of CSM2, so the one that was used in the last Intergovernmental Panel on Climate Change report. So this is a cutting edge climate model. And the hope is that if I see something big in this, that means I can then use simpler and simpler models to go back and connect with what the theoretical physical oceanographers have done in the past to try to distill out the simplest possible physics. So I started from year 1500 in the existing control simulation. I wanted it nice and spun up so that I don't have to worry about any kinds of drift. And then I immediately pulled out the Mid-Atlantic Ridge and I ran it for 100 years of simulation time. And then I'm using the last 50 years for averages. And so you actually get a really big gyre adjustment. And so what I've got, we have two main features in the Atlantic that we think about for basin scale oceanography. We think about the horizontal gyre circulations. So you have a subpolar gyre, which goes kind of like this, and a big subtropical gyre, which goes like that. So what I've got here on this top panel in pre-industrial control is in contours is the bathymetry. So that's the depth of that's where the ocean bottom is. And then in shading is a representation of that gyre circulation. It's called stream function. And so here's the subtropical gyre, and then here's the subpolar gyre. And then here's the equivalent when I take out the Mid-Atlantic Ridge. And right away, the real cool thing that I should have anticipated but didn't is just what it does to the subtropical gyre. It's so much weaker. So the colors here are much less red. By removing mountain ranges, you're making the gyre weaker. And our intuition would say it should be the other thing because we often think about friction as what's driving these kind of flows. Like if you have mountain ranges, you should have more friction. So that, mountain ranges should be slowing things down. And it turns out it's more complicated than that. It turns out that these mountain ranges are supporting flows along them that act to strengthen the subtropical gyre. And then the subpolar gyre strengthens also somewhat. And that's because a lot is you've removed this ridge over here. This is the Reykjanes ridge, and you've got flow that goes around it. So if you remove that major ridge, you don't have that big meander and you can strengthen things. Then one last bit of interest is the subtropical gyre also expands further poleward. So it weakens and expands. There's also minimal change to the overturning circulation, which was a little bit of a surprise. I expected more of an impact, but it could be just something about this one model. So something I wanted to set out to prove was that this isn't just an ocean thing, but that this is also going to impact surface climate. So what I've got here in the contours is the changes in the gyres, so the changes in ocean circulation, and then the shading is the change in sea surface temperature. And so sea surface temperature is something that we care about because this is going to impact weather, this is going to impact storms. So what you can see is where you have an increase in the gyre this way. So this is that expansion of the subtropical gyre. You're going to get warmer sea surface temperature and then colder on the other side. So you're bringing warm subtropical gyre further north on the western side of the basin, and then colder subpolar water south. And so this is going to impact, this is exactly where you have, this is the storm track in the North Atlantic, exactly where storms are spinning up and intensifying. And so this is going to impact where storms develop, how they transit the North Atlantic. Another interesting aspect is this blue area here. This is the Gulf Stream shifting southward as an impact. And it turns out, so this is, a very theoretical study, but this is an area where our climate models still really, really struggle. And so the fact that I can remove the Mid-Atlantic Ridge over here and get an interesting impact over there suggests that maybe we can think about the bathymetry, so where the bottom of the ocean is, to sort of manipulate and improve the representation of climate over there. So this is an example of where, a very curiosity-driven question, a theoretical question, could be leading us to improving our climate models in a much more applied way. Yeah, so here's the circulation change. And then finally, does this impact the atmosphere? Does this make a change in climate? And the answer is yes. So what I've got here is the change in sea level pressure and shading, and then the climatological sea level pressure and contours. So climatologically, we have an Icelandic low over here. And then so the shading is saying we're getting more low pressure on this side. So the Icelandic low is shifting southward, and we've got anomalous high pressure down here. These are on order of 1 hectopascal, which might not sound like much. But when you think about what the mean variability in this area is, it's on order 2 to 3 hectopascals. So I'm talking about the North Atlantic Oscillation, so this is actually a reasonable amount of change. This isn't minuscule. This is going to impact where weather is going in the North Atlantic. So I guess, as a bottom line, when you're thinking about these kind of global questions and trying to simulate what the climate's going to do, you really need to include all the pieces of the Earth system, because even the bottom of the ocean, matters for your climate simulation. So thanks. Happy to take questions after this is all over, and I'll move on, stop sharing my screen.
Great. Thanks, Elizabeth. That was a really nice talk. Appreciate those updates. And maybe you've copyrighted Flatlantic. I don't know, but I like the term, so thank you. Luke, we'll turn it over to you now.
Great, thanks. There you go. I think you can see it now. Okay.
We can.
Excellent. Yeah, so I'm going to talk about sort of work related to glaciers, and in particular, what we're trying to understand is how glaciers move over the landscape. The title of the talk here is Glacier Slip, the Hidden Wildcard in Sea Level Rise, because you probably don't think a lot about how glaciers move. Turns out how they move is particularly important for understanding how much ice they might discharge into the ocean and potentially raise sea level around the world. This is just a picture of a glacier. You can see at the bottom of the screen here, and then in the upper part is some sediment that was under the ice just a few months before I took this photo. So this is a map of Antarctica, and it's color coded by how fast the glaciers are moving. And the thing to notice here is that the color scale here is not linear, meaning as you go up a little bit on the color scale, you actually move 10 times faster and 10 times faster. And so there's some parts here that are moving really fast, like this spot and this spot and these spots over here. And those areas are called ice streams. And they're particularly important because even though they don't make up the majority of the land mass of a place like Antarctica or Greenland or even the Laurentide ice sheet that covered Wisconsin, they are responsible for discharging and moving the majority of the ice. And so understanding why those spots are going fast and how fast they're going is essentially the knob, in many ways, in how ice sheets can contribute to sea level rise. This is just a time-lapse photo from space for about 30 years, and it just sort of shows this, right? If you look from the top, you can see the ice is moving from the lower left to the upper right, And all that is ice flowing downhill. Just think of it as like a river, like how a river pulls water from a high elevation to a low elevation because gravity's tugging it down the hill. That's basically what happens in a glacier overall. The thing you can't tell from these images where you look from just space is what's actually giving rise to the motion. Like, how is it occurring? Is it occurring within the ice? Is it occurring in other places? Or what's exactly happening? So, this is a old diagram, but I think it's a nice one. It's probably the birth of glaciology in many respects. What you're looking at here is this would be like the surface of the glacier where you'd stand on it, and this would be in the ice, and this would be where the glacier sits on the bed beneath. And when people first started to look at this problem, they realized that some of that motion that you can see at the surface is coming from the ice actually deforming. That's like, pouring honey out and watching honey sort of slowly melt, flow down a hill if you pour it out on a board. But when they looked at how much motion you could get from the deforming ice, and then how much they actually saw the thing move at the surface, they said, something's wrong here. There must be some other way the glacier is moving besides just deforming the ice. And it turns out that a lot of the motion actually happens right at the bottom of the glacier, right where the glacier sits on what we call the bed, which is just the ground that's beneath the glacier. And in fact, those fast-moving glaciers, they have the majority of the motion occurring through this process at the bottom called slip, where it's slipping over the bedrock. Something like 90 to 95% of the motion is from this. And so a better analogy for a glacier is if you put an ice cube on a board and you tip that board and the ice cube slides down the board. And right where the ice cube sits on the board, it's interacting with the substrate, in this case, the board below it. And that friction of how it's rubbing on the board in particular dictates how fast the ice can move down the hill slope. And so we really want to understand the processes that are active right at the ice bed interface as they regulate essentially how fast the glacier can move. The thing we'd like to have to put in those types of models that Liz was just talking about is called the slip law. And that simply relates how fast the glacier moves to how fast or to how hard gravity pulls it down the hill, which seems like a really simple parameterization, but it's integral to sort of making predictions of where glaciers might move fast or where they might move slow. There's a range of different predictions of how this could work. So on the x-axis here is the slip velocity. You can think of this as how fast the glacier is moving. And on the y-axis is how much the glacier bed is able to push back and hold the glacier. Some of these just go up in unbounded ways. These are what's in those models that Liz was talking about most of the time. Sometimes we have these ones that go up and approach like an asymptotic bound. And so what this would say is the glacier bed is only capable of holding back the glacier so much. And if gravity pulls harder than that, it's going to accelerate and cause lots of ice to discharge. And so we need to know which one of these different relationships we have to put into these ice sheet models to get accurate predictions of how ice is discharged into the ocean. Now, people have looked at this, looked at the effect of choosing one of those different slip law equations and how big of a deal it makes. And so here's a paper where essentially all these model runs here are the same model. And the only thing they've changed is that slip law choice. So they've just chosen a different one of those equations. And what they find is that with everything the same, the climate the same, the ocean forcing the same, everything, they get a 50-fold difference in the predictions of how much ice will be discharged in the ocean just by choosing that one thing wrong. So that means that almost all of the uncertainty in a lot of these predictions of sea level rise is boiled down to just your choice of this one equation, essentially. So just to put it in context, here's Florida. This is a tool that NOAA makes where they show you how places become inundated. This is with 10 centimeters of sea level rise, so maybe the low end of that. And I can't turn their tool up as high as the prediction error in the predictions from the slip law, but this is the areas that would be inundated by 3 meters of sea level rise. So a lot, but still not as much as you get just by getting that one thing wrong. I'll zoom in on Fort Myers. This is where I took my kids for spring break, so I thought it'd be interesting to see what happened to this area. This is what it looks like with 10 centimeters of sea level rise. You start to see some of these areas get inundated, but this is what happens with 50 or 3 meters of sea level rise, right? The place we rented was here. It would have been underwater. Sanibel Island's all gone. This is just error simply from picking the wrong version of this slip law. And so what we like to do is determine what is the right one, like physically from physics, what is the correct one that should be used in these models. Turns out it's hard to do this. It's hard to do it in the field because there's so many things changing in a glacial system that you can't really isolate cause and effect. And it makes it really difficult to separate what's happening. Other things people have tried to do is drill all the way through the glacier and instrument the bed, but the act of drilling through the glacier introduces some complications at the bed that you can't separate what you've done from what nature would be doing on its own. So what we've approach we've taken is to build lab equipment that can try to simulate these types of processes. So this is the main machine that we use to figure this out. It's the UW-Madison cryo ring shear device. And just to explain it a little bit, this whole thing is inside of a giant walk-in freezer. And in this area right here is the sample chamber. And in there, there's a donut shape of ice that's about 1 meter in diameter. And we compress that donut on top of something that simulates at the bottom of the glacier, like sediment or till. Most of it we dig it from Wisconsin. And then we spin the ice over the till bed. And we measure how hard the till bed pushes back. And then we spin it faster, and we do it again. And then we spin it faster, and we do it again. And in this way, we can systematically build up what that slip law relationship should be. It's got all sorts of components in it. This is a 2 million to 1 gearbox ratio. The torque that's put on the system is so extensive that these giant metal I-beams literally flex in response to it. And we can measure that resistance. This whole thing is also sitting inside a tub of antifreeze, so we can regulate the temperature to within 100th of a degree. And you can see all sorts of wires coming in and out of this. We can measure basically anything you'd want to measure while these experiments are going on. The downside is they take a long time. The experiments take like 6 weeks because we're exactly replicating the conditions at the bottom of the glacier, including how fast they move. So one thing that we're particularly interested in is how glaciers slip over sediment beds. So if you go out in Madison or Wisconsin and you dig a hole, you're very likely to find some sort of sediment like this at the surface. That's because the glaciers that were here in the last glacial maximum laid them down. And not only did the glacier lay them down, but they interacted with them as they moved forward. And so we want to understand how it can move over these types of sediments because lots of those really vulnerable glaciers in places like Alaska or Antarctica in particular are sitting on beds made of this sediment. So again, here's just a diagram of the system. And so here's that ice ring that's being spun over a bed of sediment. We call it till. It's a specific type of sediment let down by a glacier, and we just measure it. So the experiment that I'll talk about is just clean ice with no debris in it, sliding over a till bed and trying to figure out how that resistance changes as we move faster and faster. What is that slip law that should be put in those models? Two potential ideas are like this. So again, sliding speed, moving that ring spinning faster and faster and faster, and the resistance on the x-axis. This one right here that keeps going up says the bed of the glacier can always push back harder, and this one says it can't, right? There's some limiting strength of, in particular, the sediment, and the sediment can only hold back a certain amount. So these are two guesses that could be in these models. This one is used in almost all ice sheet models. This one is used in relatively few. So here's a picture through the side of this thing as it's moving. It's sped up 3,000-fold, this movie. It's moving from left to right. You can see the ice on the top, and then there's sediment being moved at the bottom as the glacier's sliding over. This is probably 4 centimeters from top to bottom, and this is what the ice ring looks like when we pull it out. There's all sorts of sediment on the bottom. What the other thing we can do is measure that resistance. So here's the sliding speed on the x-axis and that resistance. And you can see that what happens is in these two different experiments, the resistance goes up and then it hits this dashed line. And then it kind of goes flat along the dashed line in both cases. That dashed line is effectively how strong the sediment is. And so the resistance of the bed can increase, increase, increase until you get to the point where that sediment starts to deform, like we saw in that movie. And then that becomes the weakest link in the chain, and nothing can be stronger than that because you have this weakest link in the chain that's regulating the whole system. So when you look back at this as these two potential slip laws, which one is it? Well, it's both. It's sort of a combination of them. It has this part that strengthens initially until you get to the strength of the sediment, and at which point after that, the strength of the sediment takes over. And it has depends on if there's big rocks at the ice bed interface or not big rocks and what it looks like. If you go out and dig a hole in the yard here, you'll probably find big rocks because the till in Wisconsin has big rocks in it, right? And that's pretty characteristic of lots of these tills or these sediments around the earth. The size of the rocks that you have in there dictates when you get to this transition point where you go from this part where the bed is getting stronger and stronger and stronger until the sediment finally breaks. And so what the composition of it is important. So you can predict a model that's kind of like this that has these components. It strengthens, that's this black part of the equation, until it gets to this point where it becomes regulated by the strength of the till. And this is called a regularized Coulomb. And so we can make model predictions based off of that estimate and compare it with our observations, and they start to do really well. And people have started to use these. Well, now it's become really prominent in modeling Antarctic glaciers. And when people have investigated this, they've shown that this slip law right here is probably the right one based off lots of different observations from Antarctica and things like that too. So it's kind of converging on these ideas. This is just a cartoon of it. So you have this glacier sliding over the bed, and what happens is these rocks that are sitting at the bed initially don't get pushed through the sediment, but as the glacier moves faster and faster and faster, it pushes on this side of the rock, and eventually it can push so hard that the clast mobilizes and it starts moving through the sediment. And you can probably see some evidence of this if you go dig around in your yard, and you can see these clasts that have been moved around in the till we have in Wisconsin too. So what some of the implications are is it gives modelers a physically based slip law and removes much of the guessing that had gone into many previous versions of ice sheet models. And one other thing is it's knowing the spatial characteristics of glacier beds, where there's a sediment, where there's not. That's going to be really important in the future to being able to make good predictions of how glaciers move and how they sort of shape the landscapes in particular. So go to Antarctica, shoot seismics through glaciers, shoot radars, waves through there. We can do all those types of things to figure this out now that we know what we need to know. So this is work funded by NSF. This is on my group. So I'm happy to stop there, Paul, and you can field any questions.
Great. Thanks very much, Luke. Really appreciate that talk on glacier slip. And thanks to all of our speakers. You are welcome now to ask questions. I think it might be most efficient if you would put them into the chat. It looks like maybe Alessandra has to forward those to everyone, but let's see. Can the speakers see the questions in the chat or no? Or is it just me? Okay. All right. Well, there are a couple questions, and so I'll start with those. And again, after these two, feel free to add more, or we can open it up if someone would rather ask one out loud. So the first one was for you, Liz. Uh, in the simulation model, did you account for the impact of volcanic eruptions? Also, some of the disturbance variables are transient and some are steady state. Did you encounter this in your modeling? So I guess maybe there's two questions there.
Sure. The simulation I'm using is not including specific volcanic eruptions. It's what's called a pre-industrial control, where you hold the radiative forcing fixed. And that's because I want to hold everything. I want to have a steady climate radiative forcing so that I can really isolate the impact of the circulation. And the other impact was I look at the transient spin up and the steady state. And yes, turns out 100 years is sufficient to get probably 95% of that. Most of the adjustment happens within the first 5 to 20 years, and you kind of see it rippling out from where you remove the Mid-Atlantic Ridge. So in the first year, you see a big impact right near it, and then you get what's called a westward propagating Rossby wave, and it's trying to figure out which way is westward for you, but it goes from the Mid-Atlantic Ridge all the way over to the North Atlantic coast, North American coast, and it hits there by about 10 to 20 years later. And then once you've got that adjustment, you're most of the way there, and you can use the last 50 years for most of it. But we are curious about how this changes decadal variability. So we're going to be extending this run for another couple of 100 years to get a better sense of not just how the mean state changed, but how is climate variability changed. Thanks.
Yeah, great. Thanks. Thank you very much, Liz. The next question is for you, Paul, and it's maybe more on the management side. For the Rock River flooding problem, can farmlands have a series of wells or other management techniques to hold the excess water and then use it when the weather causes dry seasons, such as what we've had recently?
Sure. So can farms, hold in the water and then
Yeah,
and
good
then
through
use
a
it later?
series of wells or other techniques.
Um, that's a good question. And not one that is that I am particularly knowledgeable in. Um,
I'm happy to jump in on
Yeah,
that a bit, Paul. So
probably.
I'm also involved in this study a little bit. I guess my response to that would be there's a bit of a scale issue there. We're talking about hundreds of acres that are being flooded, foot to feet deep. And so when we talk about well size or holding some of that water, on farm wells are going to be too small, right? They're not going to hardly put a dent in this. But if you look across the landscape, if you're thinking about larger wetland development or detention ponds, there you might be able to start to address some of those and capture that water and have it available later. But on-farm, individual farm practice may be a little bit too small for this scale of a problem. But it's a good question, and we have to think creatively about it for sure. I believe the next one's for you, Chris, and it says, in doing weather measurements of several variables, how do you account for measurement errors which can have a cascading effect?
Yeah. I mean, we do our best with instrument calibration, which is done each year. We've invested in, really good research grade quality instrumentation to the point that the temperature and dew point sensor is actually one that several of the Weather Service official observing airport stations are converting over to. But this is not your off the shelf from Fleet Farm weather station. So we have pretty good confidence, in the accuracy of the data that we're collecting. I would say the greater cascade of errors is actually what's happening in between stations, that have an average spacing of 20 to 30, kilometers or so. So we can't, we'll never be able to capture all of that smaller scale stuff that's going on. But, we do our best and learning more as each day goes on. So thanks for the question.
Great, great. Thanks very much, Chris. Nice set of questions. The next one's for Luke, so we're getting to hear from everyone here. The question is, are the areas of the glacier that are moving the fastest in the Antarctic sitting on top of a particular type of substrate or till?
Yeah, they are. Well, they're sitting on top of till, and so um, the areas that are moving slow are generally one of two things. They're either sitting on top of bedrock or they're sitting on top of till that's frozen, right? And so in particular, it's important for the bottom of the glacier to be what we say at the pressure melting point. It's just at the temperature that water melts at. And why that's the case is another good analogy for a glacier is like an air hockey table, right? And so if you have an air hockey table and you flick that puck, when the air pressure is up, it goes sailing across the table. In a glacier, what happens is that thing that helps buoy the glacier up is the water pressure at the bottom. The water pressure at the bottom of these Antarctic glaciers that are moving fast is so high that it counteracts over 99% of the weight of the glacier. And so those glaciers are almost floating off the bottom, which is why gravity can be so effective at pulling them down the hill. And so dialing that water pressure up or down has a big impact. And you only get that water pressure in areas that are not frozen. And so the areas that are thawed, that produce lots of melt, that can supply the water, that build up that water pressure, that's why they're moving fast. So it's a combination of they have till and they're warm enough that they're actually melting at the bottom. The coldest spot of the glacier in Antarctica is at the top, and then it progressively warms up as you get deeper and deeper and deeper towards the bottom.
Great. Thank you very much, Luke. So those are the questions that I had submitted to me so far. If there are other questions, feel free to submit those. If there are questions that someone would like to ask out loud, we're welcome to take some of those questions. We have about 5 minutes left, so we have time for a few more. Maybe while we're waiting for those, Chris, I'll ask you a question. Is the Mesonet system now complete? Would you say that all the stations are or are nearly installed? And are there more tools that may be developed or envisioned, kind of from this point going forward?
Yeah. So, yes, a large majority of the first stage of the build out is complete. Although just this morning, the team was out at the Mineral Point Airport actually upgrading, helping them out, given some failure of their equipment. So we kind of stepped up and helped them. And I guess that's a point for Flight for Life or something. I'm missing some of the details, but it's an important place, and they needed observations. There's a couple other stations up far north, associated with the Forest Service that we're taking over, but I think that just puts us at around 80 or 81. To go further from there, we would need another infuse of funding, to do so, and I'm working on that. We probably have the capacity to increase to maybe 130-ish stations that would fill in some of the larger gaps across the state. And that might be a nice goal to shoot for in the longer term. In terms of the tools you asked about, we're continually developing and advancing those. In fact, I see Dr. McNichol is on the call here. She was just hired a couple months ago to help us work through some of that. So, and we're continually getting input from stakeholders and farmers and that on new things that they'd like to see moving forward too. So I think it's that's never ending. That's probably something that will continue indefinitely. So great question.
Great. Thanks, Chris. Appreciate that. I guess I am realizing that maybe the audience doesn't have the opportunity to unmute and ask a question. I'm not sure about that. Um, I'm not seeing any more in the chat right now. I don't know if any of the panelists have any questions for each other or not.
Can I
Yeah,
ask
go
a
ahead,
question
Liz.
of Luke? How do you get a big donut ice cube? Like, how do you do that? And do you have to like change out the ice cube every time you do a new experiment? Because like if you speed it up and then you've deformed it, you kind of wrecked it. Do you have to like what does that lab process look like?
Yeah, every time we do an experiment, we build a new ice ring and we buy snow cone makers, which is an interesting thing to get through the university. I've been flagged twice for buying snow cone makers because we basically take ice and we put it in an industrial snow cone maker and make a bunch of snow, and then we put it in the sample chamber. And then we flood the snow with water that's at 0 degrees C. And what that does is it makes ice where the crystals are not all pointing in the same way. Ice has actually a crystal structure to it. And we don't want them to point the same way. We want them to be kind of random like they would be in nature. And so building it around these snow particles is how we do that process. And then we build it in the ice ring, and then we have a big engine hoist like you'd use to take an engine out of a car, and we lift it out. And then we put the bed in and make it, and then we use the engine hoist and we put it back on top of the bed. And then we push the whole sample chamber assembly into the load frame as it's sitting on a big cart essentially that has wheels on it. So yeah, it's a unique process. Yeah.
That's
Cool.
great. Great. Thanks, Luke. So we have time for one more question, and the last one that came in is for Liz. Why is the subtropical gyre so much more diffuse?
More diffuse, I think you mean in like where the stream functions were. That's a factor of the general circulation of the gyre. So it's in the you can think of it as two components in the circulation. You have what's called southward sphere drift throw, which is pretty diffuse across most of the basin, and that's set by the wind stress curl. So just how much winds you have, and that's always southward. But then it gets intensified on the western side. So this is the Gulf Stream. And that's why you see that really intense stream function just on that side. And the reason you get that is essentially because the Earth is round. Come take my class in physical oceanography and I can explain it. It takes like half a lecture to explain properly how the spinniness of the Earth and the fact that the winds are blowing it leads to an intensified current on the western sides of basins. So you see, if we have Gulf Stream, and then over in the Pacific Basin, you've got its equivalent, the Kuroshio, which are western intensified basins. So that's why you've got to kind of diffuse in the subtropics in the most of the interior of the gyre, but that intensity on the western side. I hope that kind of answered whoever's question that was.
Yeah, I think so. Great. Well, thanks again to Paul, Liz, Chris, and Luke for the wonderful set of talks that you've given for us today in the CPEP seminar, and really appreciate your time. I want to encourage everyone to check out the EarthFest activities. Again, earthfest.wisc.edu, and there's a whole slew of activities this week. So You can fill your time with that if you'd like. So thanks again, everybody. Have a great afternoon. Enjoy the beautiful weather, and we'll see you at future CPEPs. Take care. Bye.